You're watching part 2 of Motion and Energy. Please watch part 1 if you haven't done so already. Two other groups we can put energy into include electrical and nuclear energy. Electrical circuits come in both simple and complicated forms and are an important part of everyday life. We'll talk about simple electrical circuits, including batteries and resistors like light bulbs, and the type of transfer that happens in the electrical grid in subsequent slide sets. Nuclear energy we'll also cover briefly. Nuclear energy is the energy that's tied up in the deep interior of an atom. And there are two forms of it. Fission, where we break heavy elements apart, and fusion, where elements come together. Fission is what we typically use for electrical generation when we talk about nuclear power, and it's certainly the type of power associated with nuclear weaponry. Fusion is the type of nuclear energy that is contributed within the sun. The sun is actually converting hydrogen to helium, and in doing so is fusing those elements together. Both of them are, of course, releasers of energy into the environment. I have a picture on the right of a fission reactor that is active and creating this eerie blue light known as the Cherenkov effect. More on that later as well. If we think about it, our everyday lives are filled with energy transfers. I have a table of a few here, but this is by no means everything that happens to us. As we look at green plants, and you might recall from botany in life earth science, that radiant light is converted into chemical energy through photosynthesis. Animals, on the other hand, convert chemical food into heat and motion. Auto engines take chemical energy and make it kinetic and mechanical. Auto brakes take that mechanical energy and convert it to heat. Elevators take electrical energy and turn it into potential energy. Light bulbs take electrical energy and turn it into radiant energy. Electric stoves take electrical and convert it into heat and radiant energy, and gas stoves do the same thing with chemical energy. An electrical generator takes mechanical energy and turns it into electrical energy, and a nuclear reactor takes matter and turns it into heat. One topic I'd like to spend a little more time on in energy conversion is that of fossil energy. Modern society is highly dependent on fossil fuels, and I think it's important that each of us understand what is actually happening to create the fuels and how they're useful to society. As a geologist, I've spent much time thinking about this, and we could get into the complications of fossil fuel generation, but I'm going to keep it simple. What you need to start off with is organic material. I'm drawing it as a series of plant leaves here, but really the ultimate source for oil and gas are small photosynthesizing organisms, single-cell organisms, algae. You might know it as pond scum. Regardless of the matter, the trick to it is burying it under sediments and keeping the oxygen away from it. Now, this is not all that common, as oxidizing conditions can happen quite readily as the materials are laid down. But if they are reduced or preserved from oxygen, the carbon, hydrogen, and oxygen compounds that dominate organic material will convert into hydrocarbons. That's carbon and hydrogen together. And that's the important part. This usually takes some burial, heat, and pressure, but not too much heat, or you'll turn everything to graphite. This makes complex carbon and hydrogen compounds that we can then refine into the products that we use for power: gasoline, diesel, kerosene, some of the other organic compounds that we use for cleaning. All of these can be derived. We might be familiar that much of the oil in Texas is extracted from the West Texas area around Midland and Odessa. Most of the oil in those reservoirs is derived from organisms that lived 360 million years ago. So that's the geologic reason why we have these hydrocarbon compounds at depth in the Earth. A similar process works for coal as well. Let's focus on oil and natural gas, as it's the predominant source of energy for transportation. You might be familiar with units like this, the pump jack. This is installed after drilling to remove fluids from the reservoir. The fluids are oil and water typically. These get separated and then eventually refined into the products that you can buy for transportation. Different grades of octane are usually presented at the pump, but generally it's the same material, highly refined crude oil that was extracted from the ground. It's the combustion of these products that provides the internal combustion engine with its power to drive the transmission and wheels of a car. Gasoline is amazing stuff in my mind. You can propel some cars over 300 miles on just 10 gallons of the stuff. Remember, what you have to do in order to propel a car is overcome the force of air displacement, the frictional resistance in the engine and transmission and wheel parts, the frictional resistance with the force of the road, and then if you're going uphill, you're working against the force of gravity. I want to spend a minute talking about energy equivalence as used in the popular environment. We use energy every day, in the food we eat, in the gasoline we just talked about, and in the electricity delivered to our houses. However, most people are not comfortable enough with the units and scaling of energy to feel like they have any relevance in their life. This is particularly true when we have an energetic event on the surface of the Earth, a hazard like an earthquake, a volcano, a hurricane. One way the popular press conveys this is by equating it to equivalence in TNT. So what exactly is TNT? TNT is an explosive compound known as trinitrotoluene. Crystals of it are packed into explosives for constructive purposes and weaponry. 1 kilogram of TNT is equal to 4.184 megajoules of energy. That also works out to be about 1 calorie per every milligram, or 1.9 megajoules per every pound. But when we talk about the energy of TNT, that's not really what we're trying to convey. It's the energy that's released over a short time. That's technically power. Remember, energy over time is power. For comparison, consider how much energy the Earth receives from the Sun. That turns out to be 6.08 times 10 to the 17 megajoules of energy. You'll agree that's a much larger number. However, it receives it over a day's time. If we divide that in terms of seconds into it, here's the power rating for the Earth. 7.037 times 10 to the 12 megawatts. If we assume an explosion takes about 1 second, then it's still bigger than the power we would receive from TNT. So what are we really after with this comparison? I think it's really power over area. Let's go back to the Earth and sunlight example. The surface area of the Earth is roughly 5.1 times 10 to the 8th kilometers squared. And therefore the Earth receives 1.38 times 10 to the 4 megawatts per every square kilometers of sunlight. This seems like a really big number. If we apply TNT to a much smaller area on a per kilogram basis, we find that the power over the area is more substantial. A few years ago, I decided to compare the energy of a gram of TNT to other common energetic phenomena. You'll see it here on the graph. This is in a log scale, meaning that every unit is a power of 10. In other words, this is 1 in joules, this is 10, this is 100, this is 1,000,000 right here, the number 6. So every step up is an order of magnitude. That's important to keep in mind because the jumps in energy are fairly substantial. It turns out that 1 gram of TNT isn't as energetic as a gram of sugar. But again, how it's being applied makes all the difference. I told you gasoline was powerful stuff, and it too has a very high energy content per gram. But this is trivial compared to the energy in a bolt of lightning, or the average gasoline use by a US automobile in a year, or a tsunami, or an impact from a meteorite, or a volcanic eruption, be it Mount St. Helens in 1980 or Krakatoa in 1883. If you convert me in terms of my mass times the speed of light squared, which is the Einsteinian relationship between energy and matter, you get a bigger number than that. Don't try to back calculate my mass from this equation. Thank you. Bigger eruptions like Toba in 73,000 years ago, or the entirety of US energy consumption in 2001, or the 9.0 earthquake that happened in Sumatra in 2004 are much larger events. The meteorite impact that is responsible for the death of the dinosaurs at Chicxulub is still many orders of magnitude greater, but roughly equivalent to the amount of energy we receive from the sun every day. So you see, TNT is probably not a great comparison. So perhaps it's more useful to learn the units that are actually involved. We defined work in joules, and we defined energy in joules. We'll find that when we talk more about heat energy, we're going to attack it differently because the science of heat energy arose through different processes. But ultimately, we can talk about it in joules as well. So joules and then joules per second to talk about watts are going to be super important in the future. Probably the more important point here is that you can make comparisons in energy. And every system has a complicated interaction. Some so complicated it may be difficult to assess all the energy variables that are going on. But rest assured the amount of energy in it balances out. Keep in mind that joules is appropriate. Work is force times a distance. Work is also pressure times volume because they are equal. But work is not the whole energy story. Heat is going to be a big part of it as well. What we're introducing is the study of heat and motion transfer, otherwise known as thermodynamics, the Greek word for that. Thermodynamics is a very robust part of physics, and it applies to all the other sciences. None are excused from it. I'll talk more about that, but it seems that we've already covered the first law, is that energy can be transferred from one form into another. The two forms we're going to concern ourselves in the future are heat, which we're going to symbolize by Q for reasons that'll become obvious later, and work, which we were using W for. So we'll continue to use that. The first law basically states that the changes in energy can be thought of as the amount of work done from the amount of heat provided. But more importantly, it says that you can transfer heat from one form to another, you can't create or destroy it, and you are stuck with the amount of energy you have in your system. Because with the first law, we understand that there's no energy to be gained. The amount of energy we have is what we have, and it cannot be created or destroyed, even though it can be transferred around. A simple way to say it is you can't win. The first law of thermodynamics is that there is no free lunch. To conclude, we've given a lot of different names to energy, but it really doesn't matter. Energy is energy. It's all transferable. And even though we can't create or destroy it, we can certainly keep track of its changes. And that's good news, because then we know what's going on in a number of systems at a number of different scales. Much more on this later.